Welcome to this Maths Made Easy video on locating roots. To start with, let's take a look at the significance of a change of sign between f of a and f of b. Now if f of a is larger than 0, so f of a is larger than 0, and f of b is less than 0 here, then we say there's a solution to the equation f of x equals 0, and this is between the values a and b. However, this is only true if the function is continuous between a and b. Otherwise, if it's not, the change in sign might be caused by something other than a root. Furthermore, if there isn't a change in sign between two different values of x, this doesn't necessarily mean there isn't a root between these values, as the graph of f of x could just touch the x-axis between these values. So let's just take a look at a brief example then. So let's say we've got f of x, which is equal to x cubed minus 3x squared minus 2x plus 3. Okay, and what we want to do here is show that f of x equals 0 has a solution in the interval minus 1.2 to minus 1.1. So what we want to do here is show f of x equals 0 has a solution in the following intervals, so minus 1.2 to minus 1.1 here. Okay, so what we need to do here is simply substitute minus 1.2 in to f of x and minus 1.1 again into f of x. So if we start with minus 1.2 here, so in that case f of minus 1.2, well, this is simply equal to minus 1.2 cubed minus 3 lots of 1.2 squared minus 2 lots of minus 1.2, don't get any minus here, and then plus 3 there. Okay, so all we need to do now is simply evaluate this using our calculator here, and what we find for f of minus 1.2 is this is equal to minus 0.6 over 8 there. Okay, now let's consider f of minus 1.1, so f of minus 1.1, and again we just simply substitute this into f of x. So therefore we get minus 1.1 cubed minus 3 lots of minus 1.1 squared minus 2 lots of minus 1.1, and finally don't forget our plus 3 again. Okay, and if we evaluate this, what we find here is this is equal to 0.239 there. Okay, and this is exactly what we wanted to show here. F of a is greater than 0, that's our minus 1.1 here, that's 0.239, and our f of b here is less than 0, this is minus 0.648, which is clearly less than 0. So here we want to give a quick conclusion, just to summarise what we found here, and we'll give this conclusion in blue here. So therefore what we say here, so f of minus 1.2 and f of minus 1.1 have different signs, so they have different signs okay, so they have different signs, and f of x, our function here that we started with, this is a continuous function. Okay, so if we just note this as well, this is a continuous function. So what we say here is therefore there is a solution in the interval that we were looking between. So therefore there is a solution in the interval of minus 1.2 to minus 1.1 there. Okay, so that gives us everything we need there for the significance of a change of sign between f of a and f of b. Moving on now to problems with large intervals. Now when we're choosing an interval to find roots to an equation, we need to be careful that the interval is not too large. Large intervals can hide roots if there is an even number of roots in the interval, and the reason for this is because the sign would change twice within the interval. and in that case it would appear to have not changed at all. So let's take a look at this graph here on the right. So if we were trying to find a root for this graph here on the right, and let's say we chose the interval of -2 to -1 here, okay? In this case, it would appear that there isn't a root between these values, because f of -2 and f of -1 are both negative here. Okay, so we note that first. So they're both negative. However, we can clearly see here within this interval that there is a root. Okay, so that gives us everything we need there for problems with large intervals. Moving on now to take a look at functions that are not continuous. So if a function isn't continuous, like the graph of y equals 1 over x, which we can see here on the right, so this is y equals 1 over x. Now, in this case, there may be a sign change that is not caused by a root. And using this example here, and we can see it from the graph, the sign changes before and after x equals 0. However, this doesn't mean x equals 0 is a root. In this case, the sign change is caused by y equals 1 over x not being continuous at this point. So, not continuous at x equals 0 for y equals 1 over x. Okay, and we can see that here from this graph, and obviously due to the fact that if we divide by 0, that would cause us all sorts of issues. Okay, so that gives us everything we need there for functions that aren't continuous. And finally, moving on now to using upper and lower bounds. So sometimes you will be given an approximation to a root, and you'll be asked to show that this root is correct to a certain accuracy. Now to do this, what we need to show here is that the root lies in a certain interval, and choosing the correct interval is the key to doing this. So in this example here, we just simply want to show that x equals 0.641 is a root of this equation to 3 decimal places. Well, the first thing we can note here is if x equals 0.641 is a root of the equation to 3 decimal places, then the exact root r must lie in the upper and lower bounds. Okay, so in that case, our interval here is going to be 0.6405, and our upper bound here will be 0.6415 there. Okay, and the reason for this is because all values in this interval round to our approximate root of 0.641 to 3 decimal places. Now, a root lies in the interval here of 0.6405 to 0.6415. Okay, so in that case, what we need to simply do here is show f of 0.6405 and f of 0.6415 have different signs. Okay, and we know this will work because our polynomial here, our equation, is continuous. Okay, this is a continuous function. So in that case, f of 0.6405, so that would be simply 0.6405 cubed minus 5 lots of 0.6405 squared minus 5 lots of 0.6405 plus 5. Okay, so in that case, what that would simply give us here is 0.00900576 and so on. So we've already calculated these here, but do calculate these yourself and make sure you can get the same answer here. Okay, and now let's calculate f of 0.6415. See what we obtain here, and again that's just going to be 0.6415 cubed minus 5 lots of it squared minus 5 lots of 0.6415 plus the 5, and here what we obtain in this case is minus 0.0111197 here and so on. Okay, so what that shows us here, so therefore f of 0.6405 and f of 0.6415, they have different signs. So they have different signs, so therefore there must be a root between them. Okay, so therefore must be a root between them. and any value between these values rounds to 0.641 to 3 decimal places. So in that case, we know this root is correct. And that gives us the solution to our example here, and that gives us everything we need for using upper and lower bounds, and that concludes this Maths Made Easy video on locating roots.